Alright, we're going to start to cover our last and final method of integration techniques, and this is going to be one that involves what are called partial fractions. So where this comes from is actually the need to decompose or break down rational functions, n of x over d of x, into simpler rational functions that we can actually integrate. In algebra, you would be given two rational functions such as this. Like if I were to give you 1 over x plus 2 plus 2 over x plus 1. From algebra you would be asked to add this together. Well, how would you add this together? They would have to have a common denominator, x plus 2 and x plus 1. And once you realize that's your common denominator, what do? You give the first fraction an x plus 1 on top, because you have to multiply top and bottom. And then the second fraction, you need to multiply it by x plus 2. Then you have 3x plus 5 all over x squared plus 3x plus 2. Now what if I were to say integrate this function? It's kind of hard, right? However, if you had known these two separate smaller fractions and I had said integrate this, that would be a whole lot simpler, because what would this give us? Well, the integral of 1 over x plus 2 would be natural log of x plus 2, and the integral of 2 over x plus 1 would be 2 natural log of x plus 1. Then we have our plus c for a constant. This right here is near impossible. Actually, it is impossible to do the way that it is. However, when it is decomposed or broken down into two smaller, simpler rational functions, it's doable. So I'm going to give you guys some tips as to how to decompose. So to decompose n of x over d of x, first thing is, if the fraction is improper, divide first. Then you will decompose the remainder if needed. Now, if you're wondering what does it mean to be an improper fraction, well, with regular numbers, an improper fraction is something like 9 over 4, right? Where the top is bigger than the bottom, the numerator is greater than the denominator. Well, here, in terms of rational functions, it is improper if the degree of the numerator is greater or equal to the degree of the denominator. An example of that would be x cubed plus 2x plus 1 all over x squared minus 2. Okay, and even if the numerator said x squared plus 2x, that would also be improper. To divide, remember that is polynomial long division, so x cubed plus 2x plus 1. And just a quick rundown, see if you guys remember how to divide. You put x here, so x times x squared, and then x times an x. Remember, we're subtracting here, so this gives us 3x. So we're going to have 3x plus 1. So our remainder is plus 3x plus 1 over x squared minus 1. And later I can actually continue to decompose this for you guys if you need it. Okay, but this is the part that you'll end up decomposing, because for instance this would be an integral, and this would now equal to the integral of x, which you can do, plus 3x plus 1 all over x squared minus 1 dx. Alright, now some steps for actually how to decompose. First thing you're going to need to do is factor your denominator, d of x, completely over the reals. Okay, so no irrational numbers. And there's several different types of what can happen after you factor. If you have distinct linear factors, distinct meaning all different, none of the factors are repeated, and all of your factors have to be linear. Okay, so as an example, we would have 1 over x squared plus 4x plus 3. If we were to factor the denominator, we have 1 over x plus 3 and x plus 1. Those would be distinct linear factors. Another example would be if you had x plus 1 over x squared minus 2x plus 8. It's okay for your numerator to have an x plus 1 up there. This would be x minus 4, x plus 2 on the bottom. And here's the third one. We could have something like x times x minus 1 times x plus 2. So I went ahead and already factored that out. This has 3 distinct factors. We could have more. We could have 4 or 5, as long as they are all different. When you have two distinct linear factors, you are going to get two partial fractions out of it. The number of factors will determine how many fractions you have. So in this case, one of the partial fractions will contain the x plus 3, and one of the fractions will contain the x plus 1. Now, how do we know that? Let's just go back and look at the very beginning when we did this algebraic problem. Remember, if you have two of these separate ones and you add them together, you have to give them a least common denominator. And the least common denominator is made up of each of those individual ones. Now, these two on top are both going to have constants. They're both going to have a number up there. I don't know what they are, so at this point, I'm going to just put in a plus b. Okay, so for our purpose now, we're just going to identify what these partial fractions are. We're not going to actually solve for these just yet. I will show you how to solve these in a little bit. Now this next one. This one should have an x plus 4 and also an x plus 2. Again, constants a and b up at the top. Okay, and it's okay that it's an x plus 1 over here on the left-hand side. Now this third example. See how we have three factors? That means you're going to have three fractions. X, x minus 1, and x plus 2. So what do you think is going to go in their numerators? A, B, and we need a third one, so we're going to call it C. Okay, now I want you to see what happens when you have something other than a linear factor. It's possible to have distinct quadratic factors. So an example of that would be if we had, let's say, x squared over x squared plus 2. Okay, so if you notice, that cannot be factored anymore, and x squared plus 1. So these are distinct quadratic factors. So we're going to have two fractions, x squared plus 2 and x squared plus 1. And in their numerators, we're going to have a linear factor, ax plus b and cx plus d. Now, the degree of the top is always one less than the degree on the bottom. Now, I want to show you another one. What if I had x squared minus 3x on top, and on the bottom we had x squared plus 2, x squared minus 4. Do I again have just two fractions when I decompose? I actually don't, because this right here, x squared minus 4, can be further factored to x minus 2 and x plus 2. So it is not a quadratic factor. So here we would only have actually have three fractions, x squared plus 2, x minus 2, and x plus 2. So the first one is quadratic, so that's a linear factor on top. This is linear, so it has a constant on top and constant on top of the last one. The last type that we need to deal with are going to be repeated factors. So that's what happens when you have multiple zeros or multiple factors. Okay, let's try 1 over x squared times x minus 1. So in this case, I have x over here, and it's really 1 over x times x minus 1. It is not a quadratic factor like above, because I can still factor x squared into x times x, and my x minus 1 is not a repeated factor. So I should have three fractions. Three factors meaning three fractions. And they're all linear, so that means I should have a, b, and c above them. Okay, but it looks a little weird, because couldn't we just add a plus b together? We could, right? And then we would only have two fractions. But what you need to remember is if you have three factors, there must be three fractions. So we actually do something a little bit different. Whenever you have a repeated factor, we would have an x, and the next one would be an x squared. Although we do not need to put a bx plus c above it, because it is still a linear factor. So let's take a look at another one. What if I had instead 2x minus 3 over x minus 1 to the fourth power? Okay, so how many factors do we have? This is really x minus 1, x minus 1, x minus 1, x minus 1. So there are four of them. So we should have four fractions. X minus 1, x minus 1, x minus 1, and x minus 1. Because they are all linear, a, b, c, d goes on top. And because these are repeated factors, the next one will be quantity squared, quantity cubed, and quantity to the fourth. Okay, so from scratch, I'm going to decompose one problem. Okay, so here's our problem. I want to integrate x minus 1 over x squared plus x, but I can't really do this. So what I'm going to do on the side is I'm just going to write x minus 1 over x times x plus 1. Two fractions, because I have two factors. So one of them is x, one of them is x plus 1. My numerator has to be a and b, because they are constants over my linear factors. Okay, there are two methods for us to resolve this, meaning to find what a and b are. The first one that I'm going to go through is basically to get rid of your fractions. So I'm going to multiply by the LCD, x times x plus 1. So on the left-hand side, the fraction completely goes away, so I have x minus 1. On the right-hand side, I get a times x plus 1, and then b times x. In order for me to solve for this, I'm going to do what's called equating both sides, because these have to be equal. So I know the left-hand side is x minus 1, and the right-hand side is ax plus a plus bx. So I'm going to collect my like terms. That means I have a plus b in parentheses times x plus a, and that equals x minus 1. Now this method of equating both sides means that I have to make sure that the left-hand side and the right-hand side are equal. Now notice the left-hand side has one x. It must match up with the x's on the right-hand side, which is a plus b. So that tells me 1 equals a plus b. Okay, so the negative 1 has to equal the a. So if negative 1 equals a, then b equals to 2. So those are the two constants that we're missing, so that tells us what these two numbers up here are going to be. So we can rewrite our integral now, and this is going to be a, which is negative 1 over x, plus b, which is 2 over x plus 1 dx. Now the integration part is now then really super easy. This is negative natural log of x plus 2 natural log of x plus 1 dx. Sometimes you might see these answers written sort of in different forms. We could take this 2 and put it up as an exponent and combine this into a single log. So this would then read ln of x plus 1 quantity squared, and I can drop the absolute values around that because it's quantity squared, and then combine this and put the x on the bottom and make it a plus c. It is possible to also see this as natural log of some other constant times x plus 1 quantity squared over the absolute value of x. Why? Because I could say that this c equals to the natural log of c sub 1. If you were to see an answer look like this, you need to be able to recognize that all three of these things are exactly the same thing. So I'm going to stop here. If you want to see some more examples of how to solve for your constants a and b, watch the next video.